The engines were running perfectly. At 18,000 feet over gray waters of the North Atlantic, the bomber held formation, steady, disciplined, unstoppable. The sky trembled with the low, synchronized roar of radio engines. Inside, the crew moved with routine precision. Gauges were stable. Fuel lines clear. Every system green. Control, this is red leader. All checks nominal. Below them, the convoy stretched like a lifeline. Cargo ships carrying fuel, ammunition, survival itself for a nation under siege. Above them, nothing but cloud cover and the constant expectation of attack. Then it happened, a sharp metallic crack, barely audible over the engines, a flicker on the instrument panel. Not a warning. Not yet. Just something wrong. The pilot frowned. Did you feel that? No alarms. No visible damage. No enemy fighters. No flak, because the threat wasn't outside the aircraft. It was already inside. A single component, approved, inspected, signed off, began to fail. And within seconds, the aircraft that passed every test would become a falling, burning wreck. This is a story of how one small miscalculation turned a trusted war machine into a catastrophe. The vibration started so faint, almost felt imagined. A slight tremor through the control column. A whisper of instability in an aircraft that had, until that moment, behaved flawlessly. The kind of sensation pilots were trained to notice, but just as often trained to dismiss. Outside, the sky was a dull, endless gray. No horizon. No visual reference. Just cloud layers stretching in every direction, swallowing sound, muting distance. Formation flying in these conditions demanded absolute trust in instruments, in training, and in the aircraft itself. Inside the cockpit, gloved hands tightened. Check your readings again. Everything's still in the green. That was the problem. Nothing looked wrong. The engines continued their steady rhythm. Oil pressure normal. Temperature stable. Fuel flow uninterrupted. Every dial insisted the aircraft was operating exactly as designed, but the airframe told a different story. A low groan, deep within the structure, began to echo through the fuselage. Not loud, not dramatic, just enough to make the crew exchange glances. Experienced men, combat veterans. They knew the difference between combat damage and something far worse. Structural? One of them muttered. No one answered, because admitting it made it real. The aircraft had been cleared for flight hours earlier. Ground crews had signed off on every system. Maintenance logs showed no irregularities. It was, by every official standard, a safe machine. And yet, the vibration grew stronger. Not chaotic, not violent, rhythmic, like something was slowly giving way. The pilot adjusted trim. Minor correction. No response. Another adjustment. Still nothing. Now the controls felt heavier, delayed, as if the aircraft was no longer responding as a single unit, but as separate parts, struggling to remain connected. Controls getting sluggish. Behind them, the flight engineer moved quickly, opening panels, checking internal systems. His flashlight cut through the dim interior, scanning for leaks, fractures, anything visible. He found nothing, because the failure wasn't where anyone could see it. It was buried inside the structure itself. Metal under stress. Metal that had endured hours of vibration, pressure changes, temperature shifts. Metal that had passed inspection, but had never been tested like this. A sharp crack echoed through the aircraft. This time, everyone heard it. No mistaking it now. That wasn't turbulence. The aircraft lurched just slightly, but enough to break the illusion of control. Altitude began to fluctuate. The formation ahead started to drift out of alignment. Red leader, you're dropping. Correct your altitude. The radio snapped with urgency, but correction wasn't coming, because the aircraft was no longer fully controllable. Another crack, louder, closer, and then a tearing sound, like fabric being ripped apart. Except it was metal. The pilot's grip tightened as the truth became undeniable. This wasn't combat. This wasn't enemy fire. This was failure. Internal. Irreversible. And it had started long before they ever took off. By the early years of World War II, Britain's survival depended on control of the skies, and more importantly, the seas below them. The North Atlantic was a battlefield without front lines. German U-boats hunted relentlessly, targeting supply convoys that kept Britain alive. Food, oil, ammunition, everything had to cross that ocean, and protecting those convoys became one of the most critical missions of the war. To do that, the Royal Air Force turned to long-range patrol bombers like the consolidated B-24 Liberator. It wasn't British by design, but became one of Britain's most vital tools. The Liberator had what others lacked: range. With the ability to fly over 2,000 miles without refueling, it could cover the deadly Mid-Atlantic Gap, a zone where ships were once completely exposed. Equipped with depth charges, radar, and heavy defensive guns, it transformed the fight against submarines. Fast for its size, heavily armed, built for endurance. On paper, it was exactly what Britain needed, and every aircraft went through rigorous inspection before entering combat. Every boat checked, every system tested, or so they believed. One mission, early 1943. A Liberator squadron lifted off from a coastal base, heading west into heavy cloud cover. Their objective: locate and neutralize a reported U-boat wolf pack threatening a convoy. The flight began like countless others. Altitude steady, engine smooth. Inside the aircraft, the crew settled into routine. Radio chatter was calm, navigation precise. Then, without warning, a structural failure. Not from enemy fire, not from turbulence. From within, a small component, part of the aircraft's internal structure, began to crack under stress. It had passed inspection. It had been cleared for combat. But under real operational conditions, long-duration flight, temperature shifts, vibration, it failed. And once it started, it didn't stop. The crack spread rapidly along a load-bearing section of the airframe. Metal fatigue. Invisible, silent, deadly. The pilot felt it first. Subtle instability in the controls. Something's wrong. She's not holding. Within moments, the aircraft began to shudder violently. Crew members scrambled. Engineers checked panels. Nothing obvious, because by the time it became obvious, it was too late. The wing structure began to give. At 18,000 feet, there's no room for error. The aircraft lurched. One engine tore loose from alignment. Fuel lines ruptured. Then fire. A flash. A roar. Smoke filling the fuselage. Mayday! Mayday! The Liberator broke formation, spiraling downward. No enemy fighters. No anti-aircraft fire. Just gravity, and a failure no one had anticipated. Some crews attempted to bail out. Others never had the chance. Within seconds, the aircraft disintegrated midair, a machine built to survive combat, destroyed by its own design limits. From the enemy's perspective, aircraft like the Liberator were a nightmare. German U-boat commanders feared long-range patrol bombers more than destroyers, because they couldn't hide from them. Radar could detect submarines on the surface, even at night, and once spotted, a Liberator could attack within minutes. Depth charges dropped with precision. Escape was rare. To the enemy, these aircraft represented reach. Inescapable reach. But what they didn't know was that even the most advanced machines carried hidden weaknesses. The loss of that aircraft, and others like it, forced a hard realization. Inspection wasn't enough. Laboratory testing wasn't enough, because war pushed machines beyond their theoretical limits. Engineers began to study metal fatigue more seriously, how repeated stress over time could cause catastrophic failure without warning. Production processes were reevaluated. Design tolerances tightened. Operational limits reconsidered. The lessons learned were costly, but critical, because in war, the smallest flaw doesn't stay small. It grows, it spreads, and eventually, it kills. Investigations that followed incidents like this revealed a dangerous blind spot in wartime aviation. Aircraft were being pushed beyond their intended operational envelopes, not by design, but by necessity. Long-range patrols meant extended flight hours. Constant vibration from engines placed repeated stress on structural joints. Temperature variations at altitude caused expansion and contraction in critical components. Individually, these factors were manageable. Together, they created a cumulative effect no inspection checklist could fully capture. Engineers began to identify patterns. Hairline fractures forming in high-stress areas, rivet points weakening over time, internal beams developing fatigue, cracks invisible to the naked eye. The concept of metal fatigue, once poorly understood, became impossible to ignore. It wasn't about a single failure. It was about repeated stress over time. Aircraft like the Consolidated B-24 Liberator were incredibly advanced for their era, but they were also operating at the edge of engineering limits. Design tolerances that worked in controlled environments didn't always hold up in combat conditions, and the more these aircraft flew, the closer they came to failure, not from the enemy, but from the very forces they were built to withstand. The aircraft had done everything it was designed to do. It flew farther than most, carried heavier loads, protected ships that meant the difference between survival and collapse. It wasn't a failure of purpose. It was a failure of precision. In World War II, victory didn't just depend on courage or strategy. It depended on engineering, on details measured in millimeters, on calculations that had no room for error. Because when those calculations were wrong, the consequences weren't theoretical. They were immediate and irreversible. The loss of aircraft due to internal failure changed how engineers approach design forever. Metal fatigue, once poorly understood, became a central focus in aviation science. Future aircraft were built differently, stronger, safer, more resilient, not because technology advanced overnight, but because mistakes demanded it. And those lessons carried far beyond the war, into every aircraft that flies today, every system that must not fail, every mission where lives depend on unseen components holding together under impossible stress. The Liberator and aircraft like it helped close the Atlantic gap, helped turn the tide against the U-boat threat, helped secure the lifeline that kept Britain fighting. But its story is also a warning that even the most trusted machines can carry hidden flaws, that passing inspection doesn't guarantee survival, and that in the unforgiving reality of war, it only takes one small failure to bring everything down that in the years that followed. The lessons learned from these failures reshaped aviation in ways few could have predicted. What had once been considered rare became recognized as inevitable unless addressed. Engineers no longer viewed aircraft as static machines. They began to understand them as systems under constant stress. Dynamic, evolving, vulnerable. The focus shifted from simple inspection to life cycle analysis. How long could a component endure repeated strain? Where would fatigue begin? How could it be detected before it became catastrophic? These questions didn't just change wartime production. They redefined the future of flight. Aircraft design became more conservative in critical areas. Redundancies were introduced. Testing procedures became more rigorous, simulating real combat conditions instead of ideal scenarios. Because the war had proven something brutal but essential. A machine doesn't fail all at once. It fails slowly, silently, until the moment it doesn't. For the crews who flew these missions, those lessons came too late. They trusted their aircraft because they had to. Every mission demanded it. Every takeoff was an act of faith, not just in their training, but in the unseen integrity of metal rivets and design decisions made far from the battlefield. And when that trust was broken, there was no warning, no second chance, just a sudden realization that the danger wasn't always the enemy in the sky, but the flaw hidden within. Today, every aircraft that takes flight carries a legacy of those failures. Every reinforced joint, every stress-tested component, every safety margin built into modern engineering exists because something, somewhere, once broke, catastrophically, and forced the world to understand why. Because in war, progress is often written in loss, and sometimes the most dangerous threat is the one that passes every check.